Wright Field, Ohio, spring of 1927. A lieutenant colonel from the Army Air Corps Engineering Division stands 6 feet from a running aircraft engine and holds a calibrated tachometer. The needle reads 1,014 revolutions per minute. The propeller in front of him is turning, full throttle. The aircraft is producing thrust, 1,014 RPM. Every operational aircraft in the United States military inventory at that moment ran its propeller between 1,700 and 2,400 revolutions per minute. Some ran higher, none ran at 1,000. He checks the instrument a second time. The needle does not move. Then he looks at the engine itself, 4 cylinders, arranged in a cross, pointing outward like the arms of a compass, air-cooled, short, compact enough that the entire power plant, with its accessories mounted, would fit inside a footprint that a conventional 9-cylinder radial would have covered twice over. He follows the output shaft with his eyes. The shaft runs directly to the propeller hub. No reduction gearbox, no planetary gears, no intermediate mechanism of any kind between the engine's power output and the blade turning in front of it, and no crankshaft. In the spring of 1927, there was no production aircraft engine in the world without a crankshaft. Not American, not British, not French or German. The crankshaft was not a component, it was a given. The assumption so fundamental that the engineering manuals of the period did not articulate it because it required no defense. Every piston produces linear force. The crankshaft converts it to rotation. Every engine, always. The question was never whether to use a crankshaft. The question was what material, what throw geometry, what counterbalance arrangement. The man who designed this engine believed he had found a better answer to a question the industry considered already closed. His name was Harold Caminez. His answer was a cam, and what happened to that answer, and to the machine built around it, and to the men who staked careers and capital on proving it could work, is a story about what occurs when a genuine engineering insight is paired with one catastrophic structural choice, a choice that no one involved in the program was willing to reverse, not after the first test reports, not after the NACA evaluation, not after the airframes began telling them in the only language airframes have. The engine was designated the Fairchild Caminez 447C. The 447 was its displacement in cubic inches. The C identified its production variant. What it was, beneath the designation, was an engine built around the proposition that the crankshaft was not necessary. And the consequences of testing that proposition on a 4-cylinder radial in 1927 with the Army watching are what drove this machine out of the history books. But there is a question underneath that story. The question that the lieutenant colonel at Wright Field was already forming while the tachometer needle held steady at 1,014. Why 4 cylinders? Of all the ways to demonstrate a crankshaftless engine, why choose the configuration that every aeronautical engineer in the world already knew was mechanically incompatible with long-duration service? That question does not have a clean answer. What it has is a sequence of decisions made by specific people under specific commercial pressures. Understanding those decisions requires going back further than Wright Field. It requires going back to where Harold Caminez started and to the industry he was trying to change. The United States aviation industry of the early 1920s was not yet an industry in the mature sense. It was an argument between the people who believed heavier-than-air flight had a commercial future and the investors who believed the government would have to subsidize that future indefinitely before it produced returns. The war had demonstrated what aircraft could do under conditions where cost was irrelevant. The peace was demonstrating what they cost when someone had to pay. Power plants were a core part of that cost equation. A reliable aircraft engine in 1922 required skilled maintenance at intervals that would have embarrassed an automobile manufacturer. Valve adjustments, magneto timing, oil consumption that forced servicing schedules incompatible with commercial route operations. The Liberty V12 engines, surplus from the war effort, were cheap to purchase and expensive to operate. Rotary engines, which had dominated military aviation through 1918, were already obsolete. Air-cooled radials from Wright and Curtiss were improving, but they were still hand-built at price points that made commercial economics difficult. Into that environment, Harold Caminez brought a specific argument. The crankshaft, Caminez contended, was not a necessary component, it was a historical accident, the mechanism that first-generation internal combustion engineers had borrowed from steam engine practice, and that the industry had refined rather than reconsidered. The crankshaft imposed costs that the industry had normalized because no one had yet built a production alternative that worked. It added weight that did not generate power. It created a speed mismatch with the propeller that required a reduction gearbox to resolve. It produced vibration at frequencies that structure had to absorb and that instruments had to be isolated from. Every one of those costs was real. Every one of them had been accepted as the price of the mechanism. Caminez proposed a cam instead, not a novel concept in isolation. cam mechanisms of various types had appeared in engine patents since the 1890s. What Caminez developed was a specific implementation, a conjugate cam arrangement in which the pistons of a radial engine drove a central cam plate, and the cam plate drove the output shaft at reduced speed through a precisely machined load profile. The reduction was built into the cam geometry. No separate gearbox, no additional mechanical stage. The cam was the reduction mechanism and the power transmission mechanism simultaneously. The output shaft of a four-cylinder 447 cubic inch installation running this mechanism turned at 1,000 revolutions per minute under full power. Direct drive to the propeller, 120 to 135 horsepower. An assembly lighter than the equivalent crankshaft and gearbox combination. By a margin, Caminez calculated at 30 to 40 pounds. In 1923, Caminez built his first functional prototype, not a model, not a demonstration unit, a running engine under load, producing power, with a cam plate doing the work that a crankshaft was supposed to do. He had funded this himself. He had built it with his own hands, with his own calculations, with materials he had sourced independently. He ran it. It worked. Then he needed a manufacturer, and in 1925, he found one. Sherman Fairchild had built his fortune on aerial photography and then translated that fortune into aircraft manufacturing. The Fairchild FC series of cabin monoplanes was becoming a standard platform for airmail and light cargo operations. Fairchild understood the commercial aviation market at a level that most of his competitors did not, because he had been a customer of that market before he became a manufacturer within it. He knew what operators needed: reliability, fuel economy, simplified maintenance, and a power-to-weight ratio that left useful payload on the scale. Caminez came to Fairchild with hardware that produced those things. Not promises, hardware. A running engine with documented test results showing power output, fuel consumption, and operational RPM. Fairchild's engineers evaluated it. They asked the questions engineers ask. They found the answers defensible. Fairchild entered a manufacturing agreement. The engine was designated the 447C. Production tooling was cut. The first production units were installed in Fairchild FC2 airframes for evaluation under operational conditions. And then the United States Post Office entered the picture. The airmail service of the late 1920s was the most demanding operational environment in American commercial aviation. Routes ran in weather that grounded careful pilots. Schedules were enforced against conditions that no passenger carrier would have accepted. The pilots who flew airmail were experienced and practical, and the aircraft they flew were evaluated against a simple standard. Did it complete the route or not? The 447C flew airmail routes, not test flights, revenue service, real payload, real schedules, real weather across terrain that punished engines whose reliability was marginal. The cam mechanism transmitted power from four radially arranged pistons to a propeller turning at 1,000 revolutions per minute without a crankshaft in the assembly. Hours accumulated on production airframes. Routes were completed. The engine worked. That is the part of this story that tends to disappear when the 447C is discussed, which is rarely. It worked in service conditions that production aircraft engines of that era regularly failed to survive. The cam mechanism that Harold Caminez had designed in his own workshop and funded with his own resources, that Sherman Fairchild had manufactured into production hardware, was hanging beneath postal aircraft and transmitting power through a mechanism the industry said was unnecessary to a propeller that the industry said should be turning faster, 1,000 revolutions per minute. But inside those airframes, something else was also happening, something that could be felt through the structure of the aircraft rather than measured on an instrument panel, something that experienced pilots described not as noise, not as roughness, but as a presence, a character to the engine that was distinct from the mechanical pulse of a conventional radial, a vibration that built at specific power settings and that did not diminish the way turbulence fades when you climb through it. It was rhythmic, it was structural, and it was not going away. The reason was not the cam. The cam mechanism functioned within its designed parameters. The cam plate, the load profile, the output-bearing assembly, all of it performed as Caminez had designed it to perform. The cam was not the problem. The problem was something every aeronautical engineer who had studied radial engine configuration already knew. Something that had been understood since engineers first began arranging cylinders in a star pattern around a central shaft. Something that the established radial engine manufacturers had addressed decades before the 447C was conceived. A four-cylinder radial configuration is inherently unbalanced. The mathematics of this are not ambiguous, and they are not reversible through any operational adjustment. A radial engine achieves near-complete cancellation of primary and secondary vibration forces only when the cylinder count is odd. 5 cylinders, 7, 9, 14 in twin-row configurations. The firing sequence of an odd-number radial distributes combustion events around the circumference in a pattern that produces force vectors, which partially cancel each other through the rotation cycle. 4 cylinders in a radial arrangement produces a different result entirely. The cylinders at opposite positions, call them 12 and 6 o'clock, 3 and 9 o'clock, fire in pairs with a timing relationship that creates a residual couple, a rotating force pair, not cancelled by any adjacent cylinder because there is no adjacent cylinder positioned to produce the required cancelling vector, not reducible by counterweighting without introducing secondary imbalances that create their own problems, inherent in the geometry, present at every operating speed, independent of the cam mechanism, independent of the specific cylinder displacement, independent of the materials or the machining tolerances. This was not a discovery. It was a rediscovery. The engineering community had known it since before the First World War. It was the reason that production radials from Gnome, Clerget, Lerone, Wright, and Pratt & Whitney used 5, 7, 9, and 14 cylinders. Not convention, not aesthetics, physics. You cannot balance a 4-cylinder radial in sustained service. Caminez knew this. The documentation of the period is clear on this point. He knew the balance problem existed. His response, recorded in the engineering correspondence of the program, and in his communications with Fairchild, was that the cam mechanism's reduced operational RPM would lower the magnitude of the vibration forces to levels compatible with sustained service. The same imbalance that at 1800 RPM would destroy an airframe at 1800 RPM would at 1000 RPM produce forces small enough to manage. The argument was not irrational. The physics of rotational imbalance scale with the square of rotational speed. Drop the speed by roughly half, and the force magnitude drops to roughly 1/4. A force that was intolerable at 1800 might be manageable at 1000. This was Caminez's operating assumption. This was the assumption that Sherman Fairchild's engineers evaluated and found defensible. The assumption was not wrong. It was not sufficient. What the Army Air Corps found at Wright Field, what the National Advisory Committee for Aeronautics found independently at Langley, was that the vibration did not simply scale downward proportionally with RPM. The frequency shifted. The lower rotational speed of the 447C produced lower frequency vibration than a conventional high RPM engine would have generated. And that lower frequency, coupled with structural resonances in the Fairchild airframe, that higher frequency conventional engine vibration, would never have excited. The 447C was not simply vibrating. It was exciting the airframe at frequencies the airframe had not been designed to survive at sustained power settings. The engine mounts were seeing loads that the design did not anticipate. Fasteners were working loose, structural members were experiencing fatigue at intervals that no maintenance schedule had been written to address, because no production engine had ever loaded them this way. 3 seconds, 2, 1. The Army mounted strain gauges on the engine installation. They ran the 447C through its operating envelope. They measured the forces at the mounting points under sustained full power. They measured again at partial power. They measured at idle and at takeoff and at cruise. They produced numbers, and then they compared those numbers against the structural margins of the airframe. The numbers did not fit inside the margins. The NACA produced its own evaluation, 63 pages. The language is the restrained institutional language of 1920s aeronautical review. The conclusion is not restrained at all. The vibration characteristics observed under sustained high-power operation were, in the committee's assessment, inconsistent with service life requirements for operational military aircraft. They were not saying the cam did not work. The cam worked. They were saying that the cam, in a 4-cylinder radial configuration, working at the RPM and power levels required for operational use, produced airframe loading that could not be sustained. 4 cylinders, not the cam. Fairchild had manufactured the 447C to demonstrate that a crankshaft was unnecessary. The demonstration was technically successful in every respect, except the one that determined whether the engine could be used. The cam plate transmitted power. The propeller turned. The output shaft ran at 1,000 revolutions per minute. Harold Caminez's core argument was validated by every instrument at Wright Field. The instrument that mattered most was the strain gauge. And what the strain gauge said was that you cannot validate an engineering principle with the wrong number of cylinders and expect the airframe to overlook the discrepancy. After the Army evaluation closed, Fairchild had a decision to make. Redesign the program, more cylinders, different configuration, preserve the cam mechanism in an arrangement that physics permitted, or terminate. A 5-cylinder or 6-cylinder cam drive engine, properly configured, might have preserved everything Caminez had proven. The cam mechanism, the direct drive, the low operational RPM, the weight savings, the absence of a crankshaft. All of it could have survived the transition to a cylinder count that balanced mathematics permitted. What would not survive the transition was the existing tooling. The capital already deployed, the time already consumed. Redesign meant a new program with new resources, following an evaluation that had told the Army no. The commercial window that had made the 447C viable in 1925 was narrowing. The Pratt & Whitney Wasp had entered service. The Wright Whirlwind had crossed the Atlantic in Charles Lindbergh's aircraft. The conventional engine, in its conventional configuration, was improving fast, and was doing so with the institutional backing of customers who understood how it worked and could service it in the field. Sherman Fairchild terminated the 447C program. The production tooling was not transferred to a successor program. The cam plate manufacturing process, which required precision grinding to tolerances at the outer edge of what American machine shops could reliably hold in 1927, was not preserved in documentation that permitted reconstruction. Harold Caminez did not build another engine under his own name. The engineering team that had developed the cam mechanism dispersed into other programs, other companies, other work. The cam drive principle did not die at Wright Field. That is the part of this story the Army Evaluation Report could not have anticipated, and the part that makes the termination decision more complicated in retrospect than it appeared at the time. Through the 1930s, cam and barrel engine concepts appeared in European patent literature, developed independently by engineers who may or may not have known about the 447C. The conjugate cam principle was revisited in marine propulsion research in the 1940s, in applications where the balance problem was approached differently and where the cylinder counts were different. After the Second World War, swash plate and wobble plate mechanisms, mechanically related to Caminez's cam approach, appeared in helicopter rotor drive systems and in hydraulic pump designs that entered production and remained in production for decades. The argument Caminez had made in 1923, that a cam mechanism can replace a crankshaft, reduce operational speed, enable direct drive, and reduce weight, was never proved wrong. It was proved insufficient in four-cylinder radial form. That is a narrower verdict than the historical record tends to suggest. Most histories that mention the 447C at all treat the program as a demonstration that cam drive engines do not work. The Army's evaluation concluded something more specific and more instructive, that this cam drive engine in this cylinder configuration could not meet military service life requirements. Two different conclusions. The distinction matters because it determines what the 447C actually taught. What it taught was not that crankshafts are necessary. It taught that proving a crankshaft is unnecessary requires more than a working engine. It requires a working engine in a configuration that does not introduce a separate problem larger than the one being solved. The lieutenant colonel at Wright Field wrote his evaluation report in a measured hand. He acknowledged the theoretical coherence of the cam mechanism. He documented the propeller RPM. He recorded the strain gauge readings at the engine mounts. He noted the NACA concurrence with his structural assessment. He attached the photographs of the cam plate, machined to tolerances that challenged the industry. And at the end of 47 pages, he wrote two words, "not purchased." That notation sits in the National Archives, adjacent to documentation of engines that were purchased, programs that were continued, aircraft that entered service and flew for decades. The 447C file is not large. It is precise. It is complete. It is the record of something that worked in every dimension, except the one that determined whether it could be used. The engine that tried to make crankshafts obsolete is not commemorated at Wright-Patterson Air Force Base. It does not appear in standard aviation history curricula. The cam plate, machined to tolerances that represented the outer limit of 1927 American machine shop capability, smooth on one face, lobed on the other, is not on display in any public collection visible to general visitors. It is in storage, catalogued, accurate in every particular. The crankshaft is still turning in every piston engine on Earth at speeds that require reduction gearboxes or that sacrifice propeller efficiency. The weight that Caminez's cam plate would have saved is still being carried. The gearboxes that his direct drive would have eliminated are still in the nacelles. 1,014 revolutions per minute. Direct drive. No gearbox, no crankshaft. Right in every dimension that the instruments at Wright Field could measure, except one. And that one was enough to return the question to closed, put the cam plate into storage, and send the industry back to the assumption it had held since the beginning. You cannot balance a four-cylinder radial. The physics have not changed since 1927. What changed was the number of engineers who were willing to ask whether a different number of cylinders might have produced a different outcome, and to follow that question into the archives, and to read 47 pages, and to find an engine that was right about everything except what it was wrong about. That engine is still there, still catalogued, still precise, still waiting for someone to ask what it would have been with 5.